Hello again, everybody. Welcome to the last lesson of the year. Oh my gosh, we made it. Let's get busy then. Let's get this wrapped up. Going to the Secretary of State, you need to get a license plate. License plates are made up of 3 letters followed by 4 numbers. Numbers are between 0 and 9. How many unique or different license plates can be made with that format? Pause for a minute and see if you can start thinking through that. How many do you think you could possibly make so that there's not the same exact one out there anywhere else? Go ahead and pause and try that now. Well, let's start thinking about this. So we've got 3 letters and 4 numbers. So 3 letters, leave 3 little blanks there. And then I'm going to follow that with 4 numbers. And let's think about the amount of possibilities for each one of those. Now, this is ruling out like the super customized ones where you just like spell out words and stuff. So there actually are even more possibilities. But like you have to pay for those. So we're just going to keep it free. When you're picking a letter, last time I checked, there are 26 letters in the alphabet. So for each of these first 3, you have 26 possibilities in each slot. And then for the numbers, 0 to 9, you have 10 possibilities on each one of those slots. And since there's no restriction about repeating, like we could repeat 1, 1, 1, 1, you can use all 10 in any of the slots. Any one of the 10 in any one of the slots, I should say. So if you want to figure out the total number of possibilities, it's as simple as just multiplying all of those numbers together. And yeah, it's going to be a big one. But it should be, right? Like it makes sense that we should have a lot of different possibilities. And so if we multiply these things together, by the way, this is called the multiple counting principle. If you want to find the different possible ways of something happening, you can multiply the number of outcomes for each instance, and that will give you the sample space, the entire number of ways that it could happen. So if I go 26 times 26 times 26 times 10 times 10 times 10 times 10, I'm going to get 175,760,000. There are 175,760,000 different possible license plates that I could get, which again is good because hopefully we never get to the day where we have over 175 million people in Michigan. Wow, that'd be a lot. I guess they could just add another digit and then that would, put another 0 on the back. If they put one more number, just make your license plate a little bit wider or make the digits a little smaller. Then you'd have 1.7 billion. That'd buy us some more time. Anyways, let's start looking at some of these other counting techniques, some tricks. So one called a factorial is going to come into handy here. And again, a lot of these are really interesting if you want to just pause and try to work it out yourself. It's worth doing. So maybe stop, and before I show you any tricks, see what you think about numbers 2, 3, and 4, if you can figure out some sort of way that you might approach the problem yourself. Yikes. So I thought I'd start trying to just work it out by hand. Good golly, Miss Molly. That was not fun. So I did find a pattern as I was working this out, though. What I did is I kept the first letter the same, and then I knew I had 3 letters to pick from after that. So if I picked like an A second, then I had 2 letters to pick from, and then whatever's left has to go there. So I just kind of like reversed those 2, and then I put another letter here and put the last 2 there, and then I reversed those 2. Then I picked a different letter here, put the last 2, and reversed those. And that got me 6 combinations. Then I put a different letter up front and pretty much repeated that process again. Picked a letter, put the last 2 there, then reversed them. Picked a letter, put the last 2 there, then reversed them. And as I did that, I started noticing something. Whenever I start this process, I have 4 blanks. And the first pick, I can pick any of the 4 letters. But then I only have 3 letters left, then 2 letters left, and then I'm left with whatever one hasn't been used yet. And if I multiply those like I did before, I'm actually going to get the same number. I got 4 rows of 6, and 4 times 3 times 2 times 1, 12 times 2 is 24. 6 times 4, 4 rows of 6. Huh. There's actually a name for this process of multiplying the digits below. It's what's called a factorial. So you write it, weirdly enough, as an exclamation point. 4 exclamation means 4 times 3 times 2 times 1. And it's called 4 factorial. You can do any number factorial, 1,000 factorial. It would just be a gigantic number, 1,000 times 999 times 998 times 997, all the way down to 1. So it's possible. Actually, on this next one, there are 28 people in class. How many different ways can they be arranged in a line? Well, that's actually the same thing here. How many different ways can I arrange those letters? All I would have to do is take 28 and factorial. If you tried working this one out by yourself, I bet you didn't get it unless you already knew about factorials, because 28 math. Oh, if you don't know how to do this, you could sit there and go, if you have an old school calculator, 28 times 27 times 26 times 25 times 24 times, and type them all out. Yes, you could do that. I would not suggest it. You can actually on Desmos use factorial, or if you'd like to use a graphing calculator in class, we can do that as well. But all you have to do is hit 28 and then hit the math button, math, and you're going to arrow over to PRB, which is probability, and there's your little exclamation point. I think it's actually on the home screen somewhere, but I forget where. I don't know. Anyways, I hit that. 28 factorial is oof. See that E29? That means times 10 to the 29th power. So if I put 3.05, let's just round it off. It's about 3.05 times 10 to the 29th power. That would mean I'd have 305 with 27 zeros behind it. That's a big number. And it kind of makes sense, because if I was going to repeat this process here, but instead of a 4-letter word, I had a 27-letter word, not only would that make for more columns, but each column would have many more rows. Like, these lists would be humongous. Very, very humongous. Humongous among us. Similarly, think about the Powerball, the lottery. People love playing the lottery because there's a chance. There's always a chance. But what is that chance? So the way it works is there's 5 different numbers between 1 and 69, and you have to pick the exact right numbers. And then you have to pick one more that's in between 1 and 26, and that one's called the Powerball. So the odds of this actually happening would be 69 times 68 times 67 times 66 times 65 times 64. Wait, did I do that wrong? Yes, sorry. I can count. 5 numbers between 1 and 69, and then the last number is between 1 and 26, so there's 26 options there. Why don't you go ahead and grab a calculator and see how many different possibilities there are for picking the lottery. You got 69 times 68 times 67 times 66 times 65 times 26. Notice I'm not using a factorial here because I don't want to go all the way down to 1. I only want 5 of the numbers. There is a way to do that, and I'll show you here in a minute, but it's just kind of quicker to do it right here. 3.5 blah, 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 blah times 10 to the 10th power. That equals, or approximately, because I'm going to round, 3.5, 3.5 times 10 to the 10th power. I'm going to write this one out just to drive the point home. So I move the decimal once, and then I'll have 9 more zeros. So 3, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 35 million different ways over that, right? Because I rounded this number. So there's even more, but we're going to round about 35 million different ways that you could pick the lotteries. I'm sorry, I misspoke. That is 35 billion. Hundreds, thousands, millions, a billion. 35 billion different possible combinations of numbers. So if you're going to take the probability, the odds of your one lottery ticket winning the lottery, you have 1 in 35 billion chance. That's not even going to be a meaningful decimal. Yeah, it's so much less than 1%. Like 0.000000028%. Or here's a better way to think about it. If you buy one lottery ticket every day, let's take that number, 35 billion, divided by 365, it would take you around, not too long, one ticket a day. Because you're not crazy, right? You're not going to buy more than one. You're not going to throw away more than one ticket a day, more than $1 a day. It would take you about 96 million years. Now, you can't see my face right now, but I'm staring dead into all of your eyes, begging and pleading you to understand that this is a system rigged against you. Please, for every one person who wins, 96 million people lose. Don't be dumb. The odds are never in your favor. Now, permutations. There are 6 people in a race. So the idea of permutations is going to be building off this idea of factorials and looking at the way that we can arrange different things. In fact, permutation is something where the order is important. Make a quick note here so I don't forget. The order matters when you're working with permutations. And that'll be in comparison to combinations on the back where the order doesn't matter. So there are 6 people in a race. How many different possibilities are there for first, second, and third finishes? Well, if we wanted to know how many different ways we can arrange those 6 people, we would take 6 factorial. That would tell you how many different ways, kind of like we looked at up here, how many different ways I can arrange 28 people. But I only want 3 of them. So when I'm going to just choose 3 of them, I actually need to divide out, I'll show you where that comes from, the amount I don't want. I'll show you how this works here in just a second. So the total amount minus the amount that I'm going to choose. What you end up with is, if I expanded that, 6 times 5 times 4 times 3 times 2 times 1, 6 minus 3 is 3. So 3 factorials, 3 times 2 times 1. What you end up being left with is kind of like how here I only wanted 69, 68, 67, 66, 65. I didn't want the rest of them. I could have set it up this way because the lower numbers just end up getting canceled out. So I'm just left with 6 times 5 times 4, which is 20 times 6, 120. There's 120 different possibilities that out of those 6 people, we get a first, second, and third place finish. And that's what that means then, right? With the order mattering is that John, Mark, and Bill is different than Bill, Mark, and John. Like the order matters. Who gets first, who gets second, who gets third. So you always get more possibilities when you're working with a permutation because that order matters. Mark, John, and Bill would be the same as Bill, John, and Mark on a combination because it's the same 3 people. We're not concerned with what order they finish in. So that will be what we look at in combinations. But with permutation, the formula is pretty simple. The idea here is that you have n factorial over n minus r factorial, where n is the number of trials, the number of possibilities. And the number chosen is what r represents. So if you're looking for some kind of a formula for how this bad boy works, that's what you're setting up. When you care about the order, you're going to take the number of possible options. So like up here, if I want to pick 5 of the people, I would do possibly 28 people. And then in the bottom, I would have to divide 28 minus 5 because I'm only choosing 5 of them. And that would get rid of the other 23 options. 28 minus 5 is 23, right? So this allows you to figure out how many different ways you can arrange or pick things out when the order is important. Different order means different result. Go ahead and pause and see if you can work out the next using kind of that same logic. Well, starting right off, when you think about two-digit numbers being made out of the digits 0 through 9, your instinct's probably 100 because 0, 0, 0, 1, 0, 2, all the way up to 98, 99, right? 100 has 3 digits. So we include 0, 0 and stop at 99. There's 100 of them, right? But this restriction of that you can only use each digit once really does make it like one of these problems, where if I'm looking at how I can arrange people, I can only put each person in one spot. So if I'm thinking about this, I have n factorial, which in this case is 10 digits. The number of possibilities would be 10 factorial. And then with my restriction of only using one digit each, with my restriction of only being a 2-digit number, I would have 10 minus 2 factorial. So since I'm not using all 10 digits, I'm not looking at how I can arrange all 10 of them or all 28 of them. I'm only picking 2 because it's a 2-digit number. I subtract that part out and I'll have 8 factorial down here. So what that's really going to reduce to is 10 times 9, or 90. Because the times 8 times 7 times 6 times 5, that gets canceled out with what's in the bottom here. So you really end up with just this part there. And again, you could check that if you wanted to. You can use your calculator for these because you know how to do the factorial. 10 math factorial over 8 math factorial. Oh, that glare. 90. Right, so you don't have to work them out by hand like that, especially on the larger ones. You're going to want to make sure you know how to use the factorial button. All right, combination. So here, the order doesn't matter. On a combination. We actually, there's a funny coincidence, there's an error is what it is. We call those locks that you twist, like on lockers, combination locks. They're permutation locks, not combination locks, because on a combination lock, if you knew the 3 numbers, you could put them in any order. That's what I mean by order doesn't matter. If you knew those 3 numbers, like let's say the combination is 23, 18, 5, you could twist the lock to go 5, 23, 18 and still get in. That's not how they work. The order is important. You have to put them in the right order. So technically, those locks should be called a permutation lock. But yeah, math, people don't care. So here we're looking at how we can arrange Mark, Jeff, Sarah, Cora, and Dave. They want to play a game, and I need to choose 2 of them. How many different combinations of people can I choose? Well, I'm going to go ahead and encourage you to pause, and I'm going to work out, like I did on the math, all the different possibilities. But see if you can just think through it and figure out how many different ways can I pick 2 of those 5 people. All right, so I listed out all those possibilities right there. And there's not too many. What is that? 4 times 5, so 20 different possibilities. But here's the thing, is that when I have Mark and Jeff, that's the same group of people as Jeff and Mark. So again, this is where I say order doesn't matter. It almost makes it sound like you can have more possibilities, but what it does, it really restricts the duplicates. It's saying that this is the same thing that we've already got as a result here. So we're going to ignore that result. Same thing here, Sarah and Mark, Mark and Sarah. Jeff and Sarah, Sarah and Jeff. It's actually going to go down the diagonal, and all the duplicates will be in the top right the way that I organize this here. So I'm left with 4, 3, 2, 1, 4, 7, 8, 9, 10. There's 10 different ways that I can pick these people, that I can pick 2 people out of 5. And the way that this formula sets up, the way that this combinations works, is it's similar. We still have n factorial over n minus r factorial. But now we also divide by r factorial because the number that we're choosing needs to be reduced a little bit more. So in fact, we're choosing 2 here, and dividing by 2 cuts the answer you would have gotten. Like if we didn't have this r here, and then I divide by, in this case, 2, that's going to cut my answer in half. And look, it did. It cut out exactly half of my options. So that's what it's doing, is when you divide by that number that you're choosing, you're getting rid of the possible duplicates that might have shown up. So let's see how that actually works out. Again, the n means number of possibilities, and r is the number chosen. So this is like the generic formula that always works when you're doing a combination. Kind of that setup. And in this case, I had 5 people, so 5 factorial over 5 minus 2. There's 5, and I'm choosing 2 of them. And then I also divide by 2 again, so that I get rid of those extra duplicates. And when I do that, again, I'll actually show you 5 times 4 times 3 times 2 times 1 over That would be 3 factorial, so 3 times 2 times 1, and then 2 factorial is 2 times 1. And watch what cancels here. I get the 3, 2, and 1 that cancel, and I'll have 20 over 2, which reduces to a solid 10. So that last dividing by the 2 part is what just reduces us down to get rid of those extra duplicates like that. And if we were choosing more, we'd be dividing by a bigger number because there would be more duplicates. If I was choosing 3 or 4 or 5, I wouldn't just be cutting it in half. There'd be many more duplicates. And so that, conveniently enough, gets rid of those extra duplicates. Kind of interesting how that works out. So how many different unique ways are there to rearrange the letters happy? So this is similar to the math one, except the difference is math didn't have any duplicate letters. So before, I could just do a simple factorial. Here, I have 1, 2, 3, 4, 5, so I'm going to set it up as 5 factorial, but I want to divide out the duplicates. I have 2 duplicates, so I'm going to get rid of those 2 possibilities. Again, I could type this straight into the calculator. 5 factorial divided by 2 factorial. Apparently there's 60. And I can see that actually work out as 5 times 4 times 3 times 2 times 1 over 2 times 1. 2 and 1 cancels. 20 times 3 is, in fact, 60. There's 60 different ways that I could rearrange those. And what that's doing, it would be 120. 5 times 4 times 3 times 2 times 1. But 2 of the letters are the same. So I'm going to get things like P-A-Y. And then later, I'm going to get another P-A-Y. One of the pays, this is like P1 and P2, but they're the same combination of letters. And when that order matters, we don't treat those as separate entities. They are the same thing. So this is not going to be counted. We can't count that. We delete that with all the duplicates we get from the double P's. All right, go ahead and pause and see if you can work out these last two. I will tell you that the next one's pretty straightforward to what I've already shown you. The last one gets a little tricky, but pause it and see if you can work through them. So on 9, it sets up pretty similar to what I was showing you back on 7 and kind of like on 8, where you've got 12 possibilities. So that's what goes in the numerator. And we're choosing 4 of those 12. So I'll do 12 minus 4. And since I don't want to count duplicates, like red, blue, green, purple, purple, green, red, blue. I don't know if I said the same thing or not, but those would be the same 4 shirts. So we have to get rid of those duplicates. So we also divide by that extra 4, and that helps us eliminate those out just like the extra 2 did up here. So you should end up with 495, and just again to make sure you know how to calculate that, put in your fraction, 12 math factorial over 12 minus 4, which you could just do that math in your head if you wanted to. Factorial 4 math. So there you go. It's typed in just like that. Then I hit enter, and 495 comes out. Okay, so you don't have to list out all those different things like I was doing up here and cancel out. You could, if this was on the no calculator portion of the SAT, you could cancel them like that. But of course, it's always nice when you've got the calculator at your disposal. So 10, I wanted to kind of go through with you real fast, is that the real question here is how many different ways can you get exactly 2 tails out of 4 flips? So when you have 4 flips, each one of these boxes represents a flip of the coin. How many different ways can you get exactly 2 tails? Well, it could be tail, tail, and then not. Tail, heads, tail, tail, heads, heads, tail. Or heads, tail, tail, heads, tail, heads, tail, or heads, heads, tail, tail. Well, let's count. What is that? 1, 2, 3, 4, 5, 6. So there's 6 different ways. I think, right? I'm not positive. I feel like I got them all counting it out like that. Well, we can actually use our combination formula to do that. We're 4 possibilities, and I'm picking exactly 2 of them, so 4 minus 2. But the thing I want to make sure that I do is I get rid of the duplicates. Like, I can't go, if you notice when I was counting, I went 1, like this, 1, 2, 3. But then I went 4. I did not go 4 right here because that's the same. Heads, heads is the same thing as heads, heads. I've already counted when I get the first 2 flips as heads. So I have to do another 2 factorial to get rid of those extra duplicates. Because again, the order matters in this. So if I work that out, 4 factorial, and that's going to be 4 minus 2 is 2. So it's going to look a little weird, but you'll have math. 4 factorial over 2 is 4 minus 2. And then another 2 factorial. You might think, 2 times 2 is 4. Shouldn't that just equal 1? No, weirdly enough, that equals 6. And just, we're this deep. Let's go for it. 2, 4 times 3 times 2 times 1. And this would just be 2 times 1. And this is, of course, again, 2 times 1. So you can see how, let's say these cancel. And then I would have 12 over 2. And that's where my 6 comes from. So yes, there are, in fact, 6 different ways. Now, that's not what it exactly asks. That's what's the probability. So if this is the amount of outcomes that we could have, this is the amount of different ways that we can get exactly 2 tails. Well, when you flip a coin 4 times, there's going to be 2 to the 4th power different outcomes. Different ways. You could get heads or tails, heads or tails, heads or tails, heads or tails. That's 2 times 2 times 2 times 2. That is exactly 16 different outcomes, 6 of which result in you getting exactly 2 heads. So you get 6 sixteenths, or about, what is that when I divide? 37.5% chance. That's a classic SAT problem. I actually think I went over that a little bit earlier it's the crazy math I had on the board, or similar to it. Instead of 2 heads or more, or 2 tails or more, it's exactly 2, so it simplifies the math a bit. Yeah, simplifies, right? All right, well, if you have any questions on this was kind of the advanced topic. Hopefully it makes a little bit of sense. These are kind of the entryway into advanced statistics. They'll be covered again in pre-calculus, calculus, any kind of college stats class you take will definitely have permutations and combinations in it. So if you have questions, as always, let me know.